Alright, hello everybody, welcome back. So today we're going to be talking about deep neural networks and the maths behind why they work. So this isn't going to go too far into implementing actually how to code. Oh, fuck's sake. Hello everyone, welcome to the channel. So today we're going to be talking about deep neural networks. I decided to make this video because this has been something that I've been trying to learn for quite a long time, and a lot of the literature out there is very confusing, incomplete video series or explanations, tutorials and blog posts and things where the maths doesn't seem to match the code that they end up writing, or where the maths comes out as incomplete. And so I really just wanted to make this as a clarifying example of exactly what the maths behind deep neural networks is and how they actually work. So the example that we're going to be building in this series is a classic example of deep neural networks. We're going to be looking at some basic computer vision with the MNIST database of hand-drawn digits. So at the end we want to be able to feed in one of these 28 by 28 pixel black and white images into our neural network, and at the end it will tell us which digit it is from 0 to 9. So that's what we're going to try and be building, and today we're just going to focus on the underlying principles of neural networks. So this is a really basic model of a neural network, right? So we start off with a series of vectors that represent the different layers in our networks, and they are connected by these connections called weights. So in this example, I've labeled this as the input layer, the hidden layer, and the output layer. And then we've got W1 and W2 here as those weight matrices. So just to label that more completely, you can see that in this layer, we're going to take the input vector item 1, multiply that by our first weight matrix entry 1, 1, and that's going to give us some component of H1. And we do the same thing for I2 and I3, and you can see that the subscript, the first digit, matches which in the input layer it comes from, and the second digit is which in the output layer it's going to. So that's how we generate all of these, and you can see that we don't have to have layers that are the same size doing things this way. So that's an important property of the matrix multiplication we're going to be doing, is that it's not commutative, and this is a good visual example of why, because we need to have 3 inputs and we get 2 outputs, and if you reverse this then it wouldn't work, and so that intuition can be lost when you compress the vectors because you can't see how long they are when they're just represented by a single letter, but I just wanted to show that visually here. So we need to come up with a function that's going to take our input layer and this weight matrix, give us some hidden layer, and then again we want to take our hidden layer and this second weight matrix and get our output layer. So that process is called feeding forward. In a neural network, we have this idea of forward and back as an input and output, right? So we're feeding in our input vector and we're going to hope to get some output. So this is what matrix multiplication looks like in practice. All the people out there who are mathematicians watching this video, I'm sorry for the lack of notation. This is the best I can do in this software, but bear with me. So we start with our weight matrix on the left and we're multiplying it by our input vector on the right, and because this has the same height as the matrix is wide, we can do this multiplication successfully and get another vector. So you see we get here exactly what we were hoping for, where our H1 is the sum of our input 1 times this first weight matrix element 1, 1, and I2 times W2, 1, and I3 times W3, 1. Okay, and that's going to give us this nice sum to get H1. And so compressing all of this matrix and vector stuff into compressed notation, we can just see that's the weight matrix W1 times I to get H. So that's with just the weights part. The biases part is a bit like a y-intercept. If you have like a linear graph, y equals mx plus b, this is the B part. And so we're also going to stick with calling it B in here for bias. So that's got to have the same shape as our output here already, because we're not doing any transform to it with a weight matrix or anything. So we've got, again, just our simple matrix multiplication plus the bias to get H. So that's what it looks like here. So at the end of this process, you can imagine we're compressing a layer that potentially has many, many more items in it than the output layer. And what we might see as a result of that is a really gigantic output, and that could be difficult to interpret. So what happens, for example, if you get a hidden layer output with, 700, what does that mean? And so what we want is some sort of activation function which represents the way that those neurons are going to respond to an input. And so there are a few you can choose from. In this example, I'm going to use Sigmoid, and that basically will compress it into a range between 0 and 1, and then we can say, if we get a 1, then we can very strongly assume that our system is classifying it that way, and a 0 not. So for example, you might have maybe H1 tells us if it's a cat, and H2 tells us if it's a dog. We've got some picture we're feeding in. Then if H1 is a 1 and H2 is a 0, pretty confident it's a cat, and vice versa, pretty confident it's a dog, right? So what does the sigmoid function look like? And this is what it is. So it's y equals 1 over 1 plus e to the minus x is the actual sigmoid function. That's what it is. And you can see here that for all x, it compresses it to between 0 and 1. One noteworthy thing about doing a compression like that is that obviously the gradient is strictly increasing. You can see that visually here. So go left to right. The value is strictly increasing as we go left to right. And that means we don't get any oscillation or anything. And that means that the gradient is going to be mostly compressed around this area that we can see here. So you can see that as we go off really way far to the sides, we're not going to have really any gradient. And the reason why that's a problem for us when we're implementing this in code and really reasoning about how we're going to make this thing learn is that if you imagine we're way off to the side and you make some small change to try and learn and update a parameter, and that gives you a small change in x, you're basically going to get no difference in the activation, right? And so it's going to be really hard for this thing to learn, if not impossible for it to converge in a reasonable amount of time. And so you want to choose the way you initialize your weights and biases to keep your numbers roughly around 0 when they're going into the activation, and then you'll get numbers in a kind of sensible range still, but also you'll be getting some gradient to work with when you're trying to actually teach this model later on. So just an important thing to bear in mind, and of course that will differ with different activation functions, and that comes in with a kind of hyperparameter tuning thing. There's a lot of choices that you have to make when you're actually trying to implement this to solve a specific problem, and this is a more generic use case. So we're covering hyperparameters and choices and how to mitigate situations like that later in the series. So here we go. That's sigmoid. So we can show it and exactly what our representation of that is going to look like. So for convenience, this is the same as last time when we introduced this vector z, and that's going to represent an intermediate value that we can then feed into our sigmoid function to get our hidden layer. And you can see here I've just specified that the sigmoid function of the vector is actually an element-wise operation. So for each element in the vector, we're going to take our sigmoid function for that element all the way down. So these are our functions now. We've got our weight matrix times our input layer plus our bias vector gives us our vector z, and then sigmoid of z gives us our hidden layer h. So this is a concrete example. We've got the exact same model as before. We've only got 3 layers. What happens if we want to generalize this to an arbitrary number of layers where each layer could be an arbitrary size? So this model is optimized for how we're actually going to implement this in the code. I've chosen this because it makes it easier to think about later on when we implement it, but hopefully you'll all be able to follow along with me anyway. So here we go. We've got some activation A. That's what this vector now represents. So what we were calling I or H or O or whatever before, that's now our A. So these superscripts represent which layer that we're in. So you can see here we're at some arbitrary layer, lowercase l. So AL in this previous layer, which is grayed out, that's L minus 1. And this next layer over here on the right is L plus 1. Okay. So in some literature, you'll see them split the layers based on when we do the actual weight matrix multiplication. And that kind of makes sense because we're going to change the length of the vector in doing that, probably. So our activation vector here is not going to have the same length necessarily as this z vector or this b vector over here. So in some people's minds, it makes sense to segment the layers there. But again, for programming, I find this easier to reason about. So that's one of the trade-offs of representing it this way, is that we just have to bear in mind that this vector A and this vector Z and B don't have the same length, despite being in the same layer. So with this model in mind, we're just going to say that this is A of length J, then we've got B and Z of length K, and then we've got this weight matrix with the dimensions JK, and then we are going to apply the sigmoid function to take it from this Z to the activation of the next layer. So this is how we kind of define this by induction for some arbitrary layer, and for where L is 0, that's just the input to our system, so that's what we were calling I before. And when we get to L is capital L, where capital L is how many layers we've got in our specific model, that's just the output of our system. So once we get to A of L, we just stop and we just output whatever we output, and that's the end. Now we just return that. Then to just add a little extra on here, this A with a little hat on it to capital L is the expected value of AL, so the expected output. And we're going to use that to figure out how wrong we are, what the cost is of our models. So one of the things with neural networks is you need something that you're trying to optimize for, right? You need to know what your definition of correct is, and therefore use that to figure out your gradient. So we feed in some example input where we know what the output should be, and we can figure out how incorrect we were, what the cost was of making of feeding that thing forward through the system, how wrong we were. And that's just the mean squared error. So we're going to sum each item in the vector where all the items are the expected output minus the actual output squared, and that's going to then just be divided by the total number of items in that output vector. Again, mathematicians, I'm sorry, I know this looks horrible notation wise, but yeah, anyway, it is what it is. So that's our cost, and then here we've got our definitions, again defined inductively for Z and for A of L plus 1 and things. So that's how we get Z, and then sigmoid takes us from Z to the next layer. So that's how we can generalize this, and now we need to figure out how we're going to learn, how we're going to teach this thing, right? And so the only thing that we actually control in this example is the weight matrix and the bias vector in each layer. Everything else is just a calculated value based on the input, and so we need to figure out basically how much our choices for each of the elements in our weight matrix and bias vectors impacts our final output. And the technique for doing that is called back propagation. So here we go, strap yourself in, this is where it gets really fun. So we've got the same model as before, these are the same equations as before, and so what I want to do to start with is define what we're going to do and what I was just talking about with the derivatives of our weight and bias matrix. So when we learn, we're going to update our value of WL, and what we're going to do is take our current value and subtract the derivative of our cost function with respect to that WL that we currently have. Okay, and so the reason why we're doing a minus here is because the derivative with respect to W is going to take us sort of uphill away from minimizing the correctness. It's going to maximize incorrectness, right? So we don't want to do that. We want to go the opposite way. So we're going to subtract it instead of add it. And then this parameter u, that's just a scalar and like a number, you know, like I don't know, 7 or whatever. And that's just going to tell us how far we can step in that direction. And that's a thing called a hyperparameter, which just tells us how the model is going to learn. And that's one of the many choices that we have to make as we try and tune the model to the specific problem that we're solving. Okay, and then this gets a bit more sophisticated because you might want to take into account multiple examples. And so you have the cost of like multiple runs and the updates that you would make for each run, and you could maybe average those or do something interesting with those as a batch to take that step and be more confident of what direction you're trying to step in with this derivative. Okay, so that's how we can update our weights and biases is the same. And so what we want to do is start just taking derivatives of stuff and see what we can get. So for starters, I'm going to take the derivative of the cost with respect to the Z of a layer. It seems like a natural place to start. It's at the end of the layer. And so by the chain rule, we're going to be able to define this inductively. So we've got the derivative of our cost with respect to the activation of the previous layer, and then the derivative of the activation of the next layer with respect to this layer, Z. And so the derivative of this part, A L plus 1 of Z of L, is the derivative of this with respect to Z of L, which is just sigmoid prime of Z of L, and that turns out to be quite easy to calculate. That's just sigmoid times 1 minus sigmoid, I think. So it's very easy for us to calculate what that is in practice, but in the maths we can just leave it and show that it's the derivative with this little apostrophe. Okay, so I don't have to write this every time. I'm just going to use this abbreviation GZL, which is the gradient with respect to Z in layer L. Okay, that's what that represents. So let's now take the differential of C. Okay, so this colon represents the inner product between these two, and we can expand what Z is, right, because we have this expression for Z. So let's replace that here, and we get this full term, and we can expand this out element by element. So we've got the gradient with respect to ZL, inner product with the derivative with respect to WL times AL, and then we've got, same the other way around, the WL times DAL, and then this bias term here as well. And so this is the part that a lot of things seem to get wrong, which is we need to move, so we've basically got the inner product with just another thing we want to take the derivative with respect to on the far right for each of these terms. So we need to take across the term that we want to, that isn't differential. So here we've got A here transpose, and you can see that's because we moved it across the inner product here. Same with the weight matrix here, that's transposed because we moved it across, and then we didn't have to move anything across so for the bias term, so that just stays the same. And you can see then isolating all of these, we've got the derivative of the cost with respect to the weight for that layer, with respect to the bias of that layer, and with respect to the activation of that layer, and they all use this term, which is the gradient with respect to Z of that layer. Okay, so that's awesome. We've got these three equations, and what you might notice as well is that this GZ term from before was defined in terms of the derivative of the cost with respect to the activation of the layer above it. Okay, so we can propagate the error backwards. See, that's where the name comes from, back propagation. So we're basically calculating the derivative of the cost with respect to the activation of each layer, and then we can use that to find the errors, the derivative of the cost with respect to all the things we need to know in the previous layer, and keep working our way backwards. And so all we need to do this inductively is have a place to start, and that just means we need to take the derivative of this expression with respect to a of capital L to get our starting conditions. And so that's pretty easy, we just got this here, which is our expected output for the system minus our actual output, and then multiply by -2 all on k. So this part here you'll often see omitted because it's just a scalar number that we're just timesing this whole thing by, and we are also using some scalar learning rate here, and so the fact that we can just arbitrarily pick this means that we don't necessarily need to keep this part, because we could just include it again later, or it just tells us how far to go in that direction really. But the thing is, I've just shown it here for completeness. Okay, so we've got all of that, and now I want to show you what this looks like in pseudocode. Okay, so well, it's not really pseudocode because this is actual working Rust code that I've got, but anyway, so when we calculate the updates here, we can see that we're going to get all of our activations, all of our z values from when we feed our thing forward, so we have all those numbers to work with. Then our output is just going to be the very last thing in our activation array. Our cost is just going to be the mean squared error, and you can see we're just going to take the subtraction of these two vectors that we're going to map each element to its square, then we're going to sum them and divide it by its length. Okay, so that's our cost. Then we can take our gradient with respect to a of L. So I had to change this slightly because Rust doesn't like capital letters in variable names, so I've had to use AL to denote sort of a capital L, and I've used I here instead as to represent which layer that we're in. Okay, so we've got the gradient with respect to AL, and that's exactly what we've got here, -2 on k times the expected output minus the output. Then we've got our gradient with respect to a of I plus 1, which is what we need for our definition of the gradient with respect to z of L, if you remember that. So we're just going to set that initially to be our gradient with respect to AL. So just separated these for clarity. Then we've got all of our weight updates and bias updates, which are just empty vectors that we can push to. So we're going to iterate in reverse over our weights, all of our activations, and all of our z's, and we can calculate our gradient. So our gradient with respect to zi, which is gzl from up here, is exactly what we saw before. It's going to be our gradient with respect to ai plus 1 multiplied with our activation derivative of z. Then we're going to get our gradient with respect to ai here, which is weight transpose times the gradient with respect to zi. Then we can calculate our weight and bias updates, which you can see are exactly what we've got in our maths, and then we can set the gradient with respect to ai plus 1 to whatever we calculated it is for this loop, so that it's ready for the next loop. And we can just, go all the way back through all the weights that we've got and all the layers that we have, and then we just return it. So that's the pseudocode, that's how it works. Obviously there's more to it in terms of implementation, and we can go into all of that stuff, how to choose hyperparameters, how to initialize all these matrices. So for example, the biases you want to initialize all to 0, and weights ideally to standard normal in a way that's proportional to, inversely proportional to how many elements you've got in the input layer. So all sorts of things to consider, but I hope this has been helpful, and see you next time.